welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 709, to lowercase. This is a great beginner-friendly string manipulation problem that helps reinforce key concepts in character conversion. Let's dive in. In this problem, we are tasked with transforming a given string, s, by converting all its uppercase letters into their lowercase equivalents. The input string can consist of English letters, digits, and other printable ASCII characters. It is important to note that only uppercase English letters are affected by this transformation. Everything else, including lowercase letters, numbers, and symbols, remains unchanged. For instance, if we look at the first example, the input string is s equals hello. Here, the uppercase letters H and E are converted to H and E, resulting in the output string hello. Looking at the second example, we have the input s equals here. In this case, the string contains no uppercase letters, so no transformations are needed. The output remains the same as the input, here. This demonstrates that the function does not alter lowercase letters. Now, consider the third example, where the input is s equals lovely. This string is entirely composed of uppercase letters, so each letter is converted to its lowercase equivalent. Let's explore the output for this case. The output for s equals lovely is lovely. Here, each uppercase letter in the input string is converted to its lowercase form. L becomes L, O becomes O, and so on. The problem also comes with a few constraints. The length of s is guaranteed to be between 1 and 100 characters, and the string will consist of only printable ASCII characters. There are also some edge cases to consider. For example, if the string contains only lowercase letters, the output will be identical to the input. Similarly, non-alphabetic characters, such as digits or punctuation, remain unchanged. If the string contains a mix of uppercase and lowercase letters, only the uppercase letters are converted. These details ensure that the problem is well defined and that the solution is consistent across different inputs. To solve the problem of converting a string to lowercase, one simple approach is to handle each character individually. This brute force method involves iterating through the string and checking if a character falls in the range of uppercase letters, specifically between N and Z. If it does, we convert it to lowercase by adding 32 to its ASCII value, as the ASCII value of A is 32 greater than A. Characters that are already lowercase or non-alphabetic remain unchanged. By appending each processed character to a new list and joining the list back into a string, we get the desired result. This method operates with a time complexity of O, n, where n is the string length, since each character is inspected once. However, it also requires O, n, space to store the resulting string, making it straightforward but not the most efficient approach overall. While the brute force approach is simple, it comes with some drawbacks. Handling ASCII values manually can lead to errors, and the code is less readable and more verbose compared to other options. To address these issues, we can use Python's built-in .lower string method, which is much more efficient. This method directly converts the entire string to lowercase, internally performing all necessary checks and transformations. The implementation is as simple as calling s.lower on the input string and returning the result. In terms of performance, this approach still has a time complexity of O, n, as each character is processed once, but it requires only O1 additional space since the operation is performed in place. This makes it a more efficient and concise solution. The built-in .lower method has several advantages, such as providing cleaner and more concise code. It eliminates the need for manual handling of ASCII values and leverages Python's optimized internal implementation, which is likely faster in practice. However, it does lack fine-grained control over the conversion process, though this is rarely a concern in problems like this. Another alternative to consider is using a list comprehension, which is similar to the brute force approach but offers a more compact way to handle character-by-character processing. Here, we use a conditional expression inside the list comprehension to check if a character is uppercase and convert it if needed, then join the process list into a new string. This approach has the same time and space complexity as the brute force method, but the use of list comprehension makes the implementation more concise and potentially easier to read. List comprehensions offer a more compact way to implement the brute force logic, making the code less verbose. However, they still require manually handling ASCII values, which can be error-prone. Additionally, while more concise, this method is less elegant and less efficient compared to the built-in .lower approach. The built-in method remains the most straightforward solution for this problem, as it eliminates the need for manual checks and transformations while remaining both readable and efficient. While the list comprehension approach provides more control, this level of control is rarely necessary for a simple lowercase conversion task. Given the options considered, the built-in .lower method emerges as the best strategy for solving this problem. It is the simplest and most efficient approach, avoiding manual handling of ASCII values, which reduces the risk of errors. Furthermore, this method is optimized for performance, handling edge cases such as non-alphabetic characters and already lowercase letters internally. Compared to the brute force and list comprehension methods, .lower is more concise and readable, making it the ideal choice for a problem where the sole requirement is converting uppercase letters to lowercase. While the other methods offer more control, this level of customization is unnecessary in this context, emphasizing the practical advantages of the built-in approach. When we weigh the options, the trade-off with the built-in .lower method is a loss of fine-grained control. However, this trade-off is negligible for this problem, as there is no need for customization. On the other hand, the brute force and list comprehension approaches might be more educational for understanding the mechanics of string manipulation, but they are less practical for production-level code. In conclusion, the .lower method stands out as the most elegant and effective solution. It aligns perfectly with the problem's requirements, offering simplicity, efficiency, and reliability. This makes it the clear choice for solving the problem in a way that balances readability and performance. To solve this problem, we need to convert all uppercase letters in a given string to their lowercase equivalents while leaving lowercase letters unchanged. The key to achieving this lies in understanding how characters are represented in a computer. Each character corresponds to an ASCII value, which is essentially a numerical code. For example, the ASCII value for A is 65, and for A it is 97. The difference between these two values is always 32, which means that adding 32 to the ASCII value of any uppercase letter gives its lowercase counterpart. This consistent relationship allows us to efficiently transform uppercase letters to lowercase with a simple arithmetic operation. To apply this, we iterate through each character in the string, check if it falls within the range of uppercase letters, and if so, convert it by adding 32 to its ASCII value. The Python functions ord and chr are particularly useful here. Ord retrieves the ASCII value of a character, and chr converts an ASCII value back to a character. These tools form the foundation of our approach to solving the problem. Once we understand how to convert individual characters, the next step is to efficiently process the entire string. Instead of directly concatenating characters to form the result, which can be inefficient due to the immutability of Python strings, we use a list to store the processed characters. Lists are mutable, allowing us to append characters efficiently without creating new objects repeatedly. After processing all characters, we use the join function to combine the list into the final lowercase string. This method is both time and space efficient. The algorithm also accounts for key edge cases. For example, if the input contains no uppercase letters, the original string is returned unchanged. Similarly, if the input consists entirely of uppercase letters, every character is converted correctly. By leveraging the consistent ASCII offset of 32 and using a list for intermediate storage, we achieve an efficient and reliable transformation. These insights ensure the algorithm performs well across a wide range of inputs. Additionally, we need to handle special cases, such as an empty string. The algorithm is designed to return an empty string in this scenario without any errors, ensuring robustness. To summarize, the key data structure in this solution is the result list, which stores processed characters as we iterate through the input string. This approach avoids the performance overhead of repeated string concatenation. Regarding complexity, the time complexity of the algorithm is O(n), where n is the length of the input string, because each character is processed exactly once. The space complexity is also O(n), as the result list requires additional space proportional to the size of the input string. Together, these properties make the algorithm both efficient and scalable. The implementation of this logic in Python is straightforward and concise, ensuring clarity and ease of understanding. Here's how the implementation performs in practice. For example, when we pass the string ABCDE, the function converts all the uppercase letters to their lowercase equivalents, resulting in ABCDE. If the input string is ABCDE, the lowercase letters remain unchanged, and only the uppercase letters are converted, producing the output ABCDE. For an empty string as input, the function simply returns an empty string, demonstrating that it handles edge cases gracefully. These test cases confirm that the algorithm works correctly and efficiently for various inputs, including those with only uppercase letters, only lowercase letters, and mixed cases, as well as an edge case like an empty string. The provided Python implementation solves the problem of converting all uppercase letters in a string to their lowercase equivalents, while leaving other characters unchanged. Explanation. 1. Class and method definition. The solution class contains the method to lowercase, which takes a string s as input and returns its lowercase version. 2. Initialization. An empty list result is initialized to store the transformed characters as we iterate through the input string. 3. Character processing. For each character in the string s, a check is performed to determine if it is an uppercase letter, a equals char equals z. If the character is uppercase, its ASCII value is converted to lowercase by adding 32, the difference between uppercase and lowercase ASCII values. The transformed character is appended to the result list. If the character is not uppercase, e.g., lowercase letter, space, or other symbols, it is directly appended to the result list without modification. 4. Result construction. After processing all characters, the list result is joined into a single string using .join result. This ensures that the final output is returned as a string, which matches the format of the input. Key points. The approach avoids using the built-in SAR lower method to explicitly demonstrate how the conversion is done at the ASCII level. The solution processes the string in n time, where n is the length of the input string, making it efficient. Edge cases, such as strings without uppercase letters or strings containing non-alphabetic characters, are handled naturally by the logic. Example walkthrough. Input, hello world. The uppercase letters H and W are converted to lowercase, resulting in hello world. Input, Python 3.9. Only the uppercase P is converted, resulting in Python 3.9. Input, already lowercase. No changes are made as the string is already in lowercase. This solution is both straightforward and efficient, adhering to the problem constraints and requirements. Here is the Java implementation for LeetCode problem number 709, to lowercase. This solution mirrors the logic of the provided Python implementation. It uses a string builder to construct the result string and iterates through the input string character by character. If a character is an uppercase letter, it is converted to lowercase by adding the ASCII offset of 32, otherwise, it is appended as is. The string builder is used for efficient string manipulation, which is a common practice in Java. This implementation adheres to Java's syntax and conventions while maintaining the same functionality as the Python version. To begin solving the problem, we are given an input string, in this case, hello world. The first step is to initialize an empty list called result, which will be used to store the transformed characters. Now, looking at the first character, H, we determine its ASCII value, which is 72. Since H falls within the range of uppercase letters, we convert it to lowercase by adding 32 to its ASCII value, resulting in 104. The character corresponding to this new value is H, which we then add to the result list. Moving on to the next character, E, we find that its ASCII value is 101 and confirm that it is not uppercase. As such, we directly append the character E to the result list without modification. At this point, the state of result is H, E. Now, we continue processing the next set of characters, which are L, L, and O. For each of these, we check if they are uppercase, and since none of them are, they are simply appended to the result list as they are. This brings the state of result to H, E, L, L, O. Next, we encounter the character W. Its ASCII value is 87, and since it falls within the range of uppercase letters, we convert it to lowercase by adding 32, resulting in an ASCII value of 119. The corresponding lowercase character is W, which we append to the result list. Finally, we process the remaining characters O, R, L, and D. Since these are all lowercase, they are appended as is. By the end of this step, the result list is H, E, L, L, O, W, O, R, L, D. Combining all characters and result using the join method gives us the final output string, Hello World. For the second example, the input string is Python 3.9. Again, we start by initializing an empty list called result. The first character, P, has an ASCII value of 80, and since it is uppercase, we convert it to lowercase by adding 32, giving us 112, which corresponds to the character P. This is added to the result list. The following characters, Y, T, H, O, and N, are all either lowercase or non-alphabetic, so they are appended to the list without modification. At this point, the state of result is P, Y, T, H, O, N. Next, we process the characters 3, and 9. These are non-alphabetic characters, so they are directly appended to the list as is. The final state of the result list becomes P, Y, T, H, O, N, 3, 9. Joining these characters together results in the output string Python 3.9. In the third example, the input string is 123 at #ABCXYZ. As before, we initialize the result list to store the transformed characters. The first set of characters 1, 2, 3, at, and hashtag are non-alphabetic, so they are directly appended to the list. At this point, result contains 1, 2, 3, at, hashtag. Next, we process the uppercase characters A, B, and C. Each of these is converted to lowercase by adding 32 to their ASCII values, resulting in A, B, and C, which are then appended to the list. The state of result now becomes 1, 2, 3, at, hashtag, A, B, C. Finally, the lowercase characters X, Y, and Z are appended to the list as is. The final state of result is 1, 2, 3, at, hashtag, A, B, C, X, Y, Z. Joining all these characters together gives us the output string 123 at hashtag #AppSys. When analyzing the time complexity of our solution, we observe that the algorithm processes each character in the input string exactly once. If the length of the string is denoted as n, the for loop iterates over all n characters. For each character, we perform a constant amount of work, such as checking if the character is uppercase, converting it to lowercase if necessary, and appending it to the result list. Each of these operations, including ASCII manipulation, happens in O1 time. Once all characters are processed, we use the join function to combine the characters in the result list into a single string. The join operation also takes O(n) time because it concatenates all n elements. Adding these steps together, the total time complexity of the solution becomes O(n) plus O(n), which simplifies to O(n). Now, let's consider the space complexity. The solution uses additional memory beyond the input string in a few ways. First, there's the result list, which stores the processed characters. In the worst case, this list will contain all n characters from the input string, requiring O(n) space. Next, we have temporary variables, such as char in the loop and intermediate results from operations like word and chr. These variables require only a constant amount of memory, or O(1) space. Finally, the join function creates a new string of length n to store the output, which also requires O(n) space. When we combine these components, the result list, temporary variables, and the output string, the total space complexity is O(n) plus O(1) plus O(n), which simplifies to O(n). The time and space complexities remain consistent across the best, average, and worst cases. This is because the algorithm always processes the input string character by character, regardless of its content. Whether the string contains uppercase letters, lowercase letters, or a mix of both, the time complexity is O(n), because every character is processed exactly once, and the space complexity is O(n), due to memory usage for the result list and the output string. If we compare this solution to a brute force approach, where each character might be checked against multiple conditions, the time complexity would still be O(n), but with significantly higher constant factors due to redundant checks. By using a single comparison based on ASCII values, our solution minimizes unnecessary operations and achieves a more efficient implementation. Finally, let's confirm the big O complexity mathematically. The for loop runs exactly n iterations, and within each iteration, a constant amount of work is performed, making the total work for the loop O, n. After the loop, the join function is used to concatenate the list into a single string, which also operates in O, n time. Combining these two steps results in O, n, plus O, n, which simplifies to O, n, for the overall time complexity. For space complexity, the result list and the output string each require O, n, space, while temporary variables use O, 1, space. Adding these together yields a total space complexity of O, n. This demonstrates that the algorithm is optimal, as it processes each character only once and uses memory proportional to the size of the input. When working on case conversion problems, there are a few common mistakes to be aware of. First, confusing ASCII values is a frequent issue. In ASCII, the difference between uppercase and lowercase is 32. If you miscalculate this offset or misunderstand it, your manual conversion logic can fail, leading to incorrect results or even runtime errors. Another common mistake is not accounting for non-alphabetic characters. For example, directly applying conversion logic to digits or symbols can modify them unintentionally, which is often not the intended behavior. Similarly, using Python's .lower method without validating the input type can create logical issues, particularly if the input includes numbers or special characters that don't require any transformation. Lastly, inefficient iteration is a performance pitfall. Applying conversion logic repeatedly inside nested loops can significantly increase the time complexity, which becomes problematic when dealing with large strings. It's important to write efficient and well-structured code to avoid these issues. Now, another common pitfall is neglecting edge cases. For instance, inputs like empty strings, strings with only uppercase letters, or strings containing a mix of letters and non-alphabetic characters can lead to runtime errors or incorrect outputs if not handled properly. From an interview perspective, it's crucial to demonstrate your ability to handle such scenarios. Interviewers are often looking for solutions that are both robust and efficient. To optimize your code, aim for O, n, time complexity by iterating through the string just once. Also, understanding patterns like ASCII manipulation and bitwise operations can be incredibly helpful for solving not just this problem but other string manipulation problems as well. For clarity and simplicity, using built-in methods like .lower or .isupper is highly recommended, but make sure you understand how these methods work internally. Lastly, always test your solution with edge cases, such as strings that contain no alphabets, mixed case inputs, and very large strings. This demonstrates that your solution is thorough and reliable. String manipulation problems like this one often overlap with related challenges on platforms like LeetCode. For example, LeetCode 344, which involves reversing a string, or LeetCode 125, which focuses on determining if a string is a valid palindrome, share similar concepts. Additionally, LeetCode 917 requires reversing only the alphabetic characters in a string, which involves careful character handling like this problem. When it comes to alternative approaches for case conversion, the first and most straightforward option is using built-in methods, such as .lower. This approach is quick and easy to implement but might lack flexibility if you need custom behavior. A more manual method involves directly using ASCII values, subtracting 32 from uppercase letters to convert them to lowercase. While this gives you more control, it is prone to errors and can make your code harder to read. Finally, there's the bitwise operation approach, where you use the OR operator to set the fifth bit of a character. This method is extremely fast and efficient, but it's less intuitive and rarely used in interviews. Choosing the right approach depends on the problem requirements and the trade-offs you're willing to make between readability, flexibility, and performance. Great job following along. In this session, we reviewed the problem to lowercase, discussed its solution, and highlighted key takeaways. Keep practicing string manipulation problems to sharpen your skills. Thank you for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!